Hello everyone. Good morning. Welcome to this session. Can somebody please confirm whether I'm audible and my screen is visible or not?
Yes, ma'am.
Okay, thank you. All right, so let's get started. So today in this session, what we're going to cover is Perceptron. Okay, so I'll give a very brief introduction to Perceptron and the algorithm that uh, Perceptron follows, and then we are going to implement that algorithm. Okay, so Perceptron is a kind of algorithm that has a very strict condition that it works only on linearly separable data. Okay, so as you can see here, this is an example of a linearly separable data, which means you take a you take a line, and just using that line, you'll be able to completely separate the two classes. Right? That's the linear separability, roughly speaking. So there'll be some equation of this line, which is W transpose X, right? There's some weight vector, and using that, we'll obtain this line W transpose X. Wherever W transpose X is greater than equal to 0, we predict a class to be +1. Wherever W transpose X is less than 0, we predict the class to be -1. So generally in Perceptron, we take classes to be +1, -1, but it doesn't matter. We take this so that we can match it with the sign of W transpose X. As you can see, if the sign of W transpose X is +1, we give a +1 class and so on. So it matches with that, but doesn't matter. You can also proceed with 0 and 1. Doesn't matter. So this is the basic requirement that Perceptron has. On the other hand, this, as you can see, is an example of non-linearly separable data, which means there's some noise in the data in the terms of the data points of one class being present on the other side of the line. Okay, for example, these two are the data points which are on the wrong side. So this is an example of non-linearly separable data. If you apply perceptron algorithm on such a data, of course you can proceed. You can mention some number of iterations. It's an iterative algorithm, as you might know. So you can specify the number of iterations that it should try out, but then it will never be able to completely separate the data, because what we are using is a linear decision boundary. And of course, you can see that the linear decision boundary cannot separate data, something like this, right? So in this case, the perceptron algorithm will give an error of 0, because it will be able to completely separate them. On the other hand, in this case, there'll be some error, right? Because it will never be possible to divide them using a linear decision boundary. Okay. Now let's look at the steps of the perceptron algorithm, which we'll be just now implementing. So what is the input? We are given the data. It's a supervised learning technique. So we are given the labels of each data point as well. So x1, x2, x up to xn, these are the feature vectors, and y1, y2, yn, they are the target labels. It's a classification problem. The vectors can contain d features, and yi can be any value out of +1 or -1. So this is a positive class, this is a negative class. Now this is the sequence of steps that we follow. We initialize some weight vector. So it's an iterative algorithm where the iterations will start from 0 to some number, let's say t. Now 0 is actually not an iteration, it's an initialization for w, right? So initialization of w will make it to 0. In practice, you can start with any arbitrary value of w, that will also work. So in lectures, we had taken w to be a 0 vector, so that's what we'll be using. But I'm telling you, you can practice and you can explore later that any other value for w will also work. Now, after initializing w to a 0 vector, we run some number of iterations until convergence. We'll talk about what convergence is here. Now, in each iteration, we perform two steps. The first step is we pick some data point from the data. So let's say we are given x1, x2, x3, x4. So we will pick them one by one. First, we'll pick this one, and we'll check something. What do we check here? We check the sign of W transpose Xi. So this is WT. WT means the value of W in the iteration T. Okay, in general, this is the value of W in Tth iteration. So we are taking a transpose of that. So this is nothing but W transpose Xi. We check the sign of W transpose Xi. If that is matching with the label Y, we don't do anything. That means with the given W, we are able to correctly predict for this data point. In case this sign doesn't match, what do? We apply this update rule. This is called the update rule of Perceptron. It might be good to keep this in mind. Now, what is this update rule? Wt plus 1 is equal to Wt, which is W new, W old, right? W new is equal to W old plus Xy. Okay. So, please note that this Y refers to the actual target. Okay. Y refers to the actual target. So, which means if the actual target was plus 1, this update rule will become Wt plus 1 is equal to Wt plus Xi. On the other hand, if the actual target was minus 1, then the update rule will become Wt minus Xi. So these are the two versions of the update rule that we are going to follow in case of mistakes, right? So you know that there can be two kinds of mistakes. One, when
No,
the,
I,
yeah,
I want a small clarification here.
go on.
Uh, do we apply the WT plus one for the all XI
No, we'll do it one by
after?
one. No, so for, let's say this is the given, value of W that we start off with. It's
Okay.
not that we'll apply this W on each and every data point. It's not like that. We go step by step. We follow some sequence in the data. So let's say this is the data that we have, x1, x2, x3, x4. We will be predefining that this is the sequence that we are going to follow, which is first we'll apply this W to x1. We'll see whether there is any mistake or not. If there is no mistake, we don't do anything, right? If there is any mistake, we update this W. And with this updated W, we move to the next data point. If there is no mistake, we don't do anything. We move to the next data point with the same copy of W. Okay. In case there is a mistake here, once again, we update the W. Okay. Is
And
the
this updated W will we won't apply to X1 and X2 again,
no,
right?
no. So this
Okay.
is one iteration. This is also called epoch or an iteration, right? So once one iteration is over and we have made some number of mistakes and accordingly we made some number of updates, we go back here. Okay, we go back here. We once again, so there's a running copy of W, please note that. So with the W, which was the latest, which came from here, we move with that copy of W to the first data point in the next iteration. And once again, we do the same. If you find that there are no mistakes that were found in a given iteration, we stop there. Okay, that's precisely what is called conversions.
Ma'am, there is one confusion here.
Yeah.
So actually, suppose we have one W, whatever W is, and
Hmm.
we are doing this. We are calculating XI no, WT XIs. Okay, ma'am.
This
Sign
thing.
of WT. Yeah, yeah,
Yeah. Yeah.
yeah. We are doing it, and maybe that there are more than one data points which give us mistakes. Okay,
Hmm.
like
Right.
x2 and x3.
Hmm.
So we have to add only the first one which occurred, or we have to add in WT. We have to add xi yi na. So suppose x2 and x3 there are two mistakes.
Hmm.
So and we encountered the first mistake through
Hmm.
x2. So we
Correct.
have to add x2 y2
Only.
only
Only
one.
X2. Yes.
And if by chance I means the mistake occurred x3 first, then
Okay. Hmm.
I will update from that only.
Correct. So that's what I'm
Whichever
saying.
whichever is getting first.
Correct. So there's some sequence that we are going to follow. So let's say we are going to follow this sequence. This will be predefined. So in every iteration, we are going to follow that sequence. So that's why I told you we are going to follow this sequence x1, x2, x3, and x4. Now, getting back to what you were stating, let's say there are two mistakes, x2 and x3. firstly, you will not go up to x3 immediately, right? You will go step by step. You will only check one data point at a time. You will not check multiple data points with one value of w. Okay, so with this value of w, you will not, let's say you're starting off, okay, with this value of w, you will not check all data points x1, x2, x3, x4. No. So that's why it's written pick one pair and check only on that pair. Okay, so we, with this w, we check x1. If there is a mistake, then we update this w, and to the next data point, this updated copy of w will be applicable. Is that clear?
Yes, yes, ma'am.
In doing so,
Yes.
it may be the case that probably the mistake has been already handled. So we don't get any mistake on x2. The other cases, we still get a mistake. In that case, we once again update this value of w, and with this updated copy of w, we move to the next data point and so on. Is this clear? Any doubts so far?
One
Because
more thing, ma'am. One more
yeah,
thing.
yeah.
Suppose we encountered a mistake on x2 and we
Hmm.
updated our w, then we will start over again from x1, or we will just move off to
Now
x3.
you will move forward. Okay, you will finish the
But
complete
maybe
iteration,
okay, and
and
then
then you
maybe
come
I
back
will
here.
come back here.
Yes.
So again, maybe I can get an error, or maybe not.
Yeah,
Whatever.
maybe not. Yeah, yeah. It could be or could not be. Yeah. So in doing so, if there is an iteration where you did not find any mistake, that's when you can say that we can stop, and that's what is called convergence. Is that clear? Any
Yes,
doubt?
ma'am.
Anyone? Any other doubt so far? Because this is precisely what we are going to code. Okay, so this should be pretty
Ma'am,
clear to everyone. Yeah, go on.
yeah, ma'am. Is it necessary that always convergence happens? Because as per this algorithm, we are assuming that convergence will always happen.
Yes, the convergence will
Uh,
always happen. There is actually a proof behind that, and that proof is
it will
focused
be
on,
margin, then only it will converge.
right,
Otherwise,
correct.
maybe
There should be a gamma margin. So so given that this is coding session, I should not get into the details of that proof, but briefly I will tell you that that proof focuses on finding the total possible number of mistakes that can happen given a data set. Okay, and that is a
Okay.
uh, finite value. Okay, if you were there in yesterday's session, so there was a similar thing for k means also. Here also there will be a limit on how many mistakes can take place, and that is a finite value. That is what we prove. Okay, and that indicates that the perceptron algorithm is always going to converge. Okay, all right, so this was the introduction. Yeah.
Uh, Convergence means W value won't change like after every iteration,
Yes.
right?
When does w change? Whenever there is a mistake, right? Correct.
Correct.
So implicitly it means that convergence will happen when there were no mistakes that were found in an entire iteration. Is
Okay.
that clear? Okay, any other doubt in this whole thing, this algorithm? If it is clear to everyone, we are good to proceed. So now I'll move on to the code and we'll start coding. Okay, this Colab just contains the kind of questions, the steps that we are going to follow. And it is there in the drive. If you want me to copy the link, I can paste it in the chat. Okay, screen is not visible, is it? Okay, yeah, it is visible. All right. All right, so this is what we are going to follow. First, we have to create a data set, right? So here,
ma'am, here sklearned library is used only for the purpose of this defining x and y, and or I mean, we were supposed to do this thing on NumPy.
yeah. So yesterday I actually created a data set using NumPy, right? If you were there in
Yes,
K-mean
yes,
session.
yes, yes,
So
yes.
you can do that also. I just, so here I'm using sklearn.data sets just to generate the data. Okay. So we are just generating some data, and there's a reason why I'm following this, because it will be quick uh, to create two kinds of data. One that is linearly separable, another that is not linearly separable. I'm going to show you both the cases. So it's just to create the data set. But if you want to create the data using NumPy, you can follow yesterday's session. There we had used numpy.random.randn to generate the data. Okay, you can follow that also.
Yes.
All right, so just a brief intro to this library, because we are going to generate data from it. sklearn.data sets is what we are using, and in that there is make underscore classification library, which can be used to create a classification data set. Okay, now there are several attributes to this class make underscore classification. First is the number of samples that we want to create. So we are going with 50 samples here. And then the number of features I'm taking to be 2, so that we can visualize the data set. If it is more than that, it will be difficult to visualize. So we are explicitly keeping only 2 features. Now there are a couple of more parameters, attributes pertaining to the features. So in general, out of all the features, it is likely that some of the features may not be informative. Okay, there are very few features which are informative, which have a good correlation with the target. So they are called informative features. And some features are redundant features also. In any data set that you take in general, in real world data, some features are not useful, okay, and we tend to remove them. So this is a general library which can create different kinds of data sets for us, right? So I'm specifying that both these features should be informative. Out of these 2 features, both of them should be informative is what I'm saying, and there should not be any redundant features. So these are the values that I'm passing. And number of clusters per class I'm taking to be 1. You can have multiple clusters in a given data. So to keep it simplistic, you can just go with 1 cluster per class. So that the data pertaining to a given class will not be too much scattered. That's the effect of this attribute. Now another one is flip y. I'm going to use it later on also to generate a not linearly separable data. So that's why it will be good to know about it as well. Flip y means how many data points should be assigned a class randomly. Okay, so I can actually quickly show you this thing, just to tell you how it will generate a linearly separable data. So flip y is the fraction of samples whose class is assigned randomly. Okay, which means noise, how much noise you want to introduce in the data. We don't want any noise because we want a linearly separable data set. So I put it 0. Class separator, how much should be the margin between the data points belonging to 2 classes, and then some random state I'm passing. So this is what I'm executing. Now you would have gotten X and Y.
So, ma'am, if we want a non-linearly separable data,
Hmm.
then we will certainly use y values. Means y
Flip
is equal
y.
to something. Yeah, flip y.
Yeah, correct.
And then that case, if we put flip y is equal to 1, then only one non-separable point will be there. It is
No, flip y
that,
is a fraction. So if you see here, it's a fraction of
okay.
samples. So
So
1 means all of them will be assigned randomly.
okay,
So there will
okay,
be too
okay.
much noise. That will not be
So
good data.
0.1 or 0.2, like
Correct.
that I will.
Correct. Yeah. All right. So this is the
And
kind of
ma'am, class separator is the gamma value.
Gamma margin.
sorry, class separator. No, it's
Class
the
separator
total
C,
distance between the data points belonging to 2 classes.
total distance means I'm not getting. Is it something related to gamma margin?
So let me do one thing. Yeah,
It will
it's
be
relative, but
twice.
not exactly equal to gamma. Yeah,
Will be
twice you can
twice.
say. You can say
Or
twice, because gamma is on both sides, right? Gamma on
and
one
ma'am,
side.
one more thing, if gamma is grounded to be, means, that is fixed to 1,
Hmm.
then it is the W, which is the width between the means both the cluster or
Yeah,
classes.
kind of. Yes.
So yeah, so in that scenario, I don't understand. W should be, I mean, if gamma is 1 grounded to 1, then gamma margin from both sides, means from the
So
linearly
gamma can be
separability.
anything actually. Gamma can be anything.
No,
Uh,
in class actually, when we were proving that
no, the length of
so
the length
length,
of
yeah.
weight vector to be 1. that was length of weight vector to be 1. Gamma could be any value. If you are
Okay.
referring to the proof of perceptron, then we had taken this simplification that the length of weight vector should be 1. Okay, gamma could be any value.
Okay.
Maybe you might want to revisit that.
Yeah, sure.
Okay, so this is the kind of X that got created. There are two features, as you can see, and you can also cross check. So how can I see how many samples are there in X? Can somebody tell me from the previous classes?
X dot shape.
Yes.
Yeah, X dot shape will give us what? Will give us the both the things, number of data points and the number of features. So if I write X dot shape 0, I'll get the number of features, sorry, number of data points, samples. And if I write X dot shape 1, you get the number of features. You can just cross check. I mean, given any data, here we have generated ourselves, so it is clear, but in general, you might want to see. Okay. Like I told you, we generally
By
stick to
default, here always this matrix is n cross d.
N cross D, yes. It's N cross D, yes. Okay, so in the target vector Y, replace all occurrences of 0 with -1. Whatever you studied so far in NumPy, would anybody like to tell me how we can do this? So our Y, if you see, let me print that also. Our Y vector is like this. Okay. So what we want is just to stay, keep it uniform with the kind of algorithm that we have discussed. We might want to replace 0 by -1. That's what we want to do. How can we do
we
this?
use that boolean means 0 is equal to true.
That will
Can
be
it be
huge,
slash
right?
function or replace
Yeah.
function?
Yeah, there are actually several ways to do it. We
We
can
can
follow
do
several
NP
ways.
where we can do NP where if the condition
NumPy
is
dot where, yes.
yeah.
So before, so everywhere you have to pass a condition, right? So if I do y double equal to 0, what should I expect? What is it that I'm getting?
It's a Boolean vector.
It's a Boolean vector, so it's kind of broadcasting again. So the 0 is being checked with each value of y. Wherever it is 0, we get a true. Wherever it is 1, we get a false, right? Now, this Boolean vector we got, right? And yesterday we studied that we can pass a Boolean vector inside the NumPy array itself, okay? And wherever true is there, we want some effect to take place. What is the effect that we want to take place here? We want to replace that by
-1.
-1. So I'll write equal to -1. So when I do this, so let's see what is y. All the values, the 0 values in y will be replaced by -1, right? Now our classes are -1 and 1, okay? All right. Now, if you want to see how many unique classes are there, this is,
after breakfast after chapati.
please mute yourself if you are not speaking to me.
So
Okay.
we always need to do this. Means 0 will not work because multiplying with 0 will give the 0. So we have to change zeros to -1.
See, if you are using that y multiplied by w transpose x, right? That
Yes.
notation you're using, that expression you're using, then if you have y is equal to 0, then this will not work, right? You should have either +1 or -1. But in general, if you are not using this expression, so we are actually referring to lectures, maybe some people might not be connected to them. But what I'm saying is, in general, you can use 1 and 0 as well. So it's just that we want that sign should match. That's why we are keeping them like this for convenience. But you can try out that you can use 0 and 1 as well. We're just trying to follow the uniform notation, so we are sticking to it. Okay. How many unique classes are there in the target vector? If you have to see, what should I write?
So ma'am, one more thing. If
Yeah,
we
yeah,
are
go.
using 0 and 1,
Hmm.
then instead of giving the sign, it will give result will also will give the 1 and zeros.
Yeah, correct. So
Yeah.
yeah, so here, so you will just replace this statement, right? So since the sign is not going to match if you are having 0 and 1 classes, so you will write it differently, which means if wt transpose xi is equal to, is greater than equal to 0, okay, and then you will test it with y separately, right? Then yi should be y if these two should match, right? These two should match. On the other case, wt transpose xi less than 0, in that case yi should be 0. If these two match, then you don't do anything. If they do not match, then you apply the
Okay.
subnet rules. You just rewrite these two, that's
Yes,
all.
yes,
Okay,
yes, yes.
so in the code also, when you convert this algorithm to code, you will accordingly write these two steps. It is going to work as well. Okay, all right. Now there's a function unique. I don't know whether you used it earlier or not. So if in an NumPy array you want to see what are the unique values. Okay, I didn't do this, is it? All right, let's import both matplotlib as well as NumPy. Okay, so numpy.unique is a function that you can, that's very handy. So let's say you get some data set. Here it is straightforward. We know there are two classes, but in general, you might want to see the number of unique values in any given vector, right? So if you want the number of unique values, you'll write, and okay, this is in pandas. Okay, that is pd.n unique. All right, so in NumPy, this unique is going to work only, which will give you all the unique values. So here there are two unique classes, that is fine. Let's proceed. How do we plot this
Ma'am,
data?
return counts can be done to see how many.
Which ones? Sorry.
np.unique y comma return counts equal to true.
Yeah, definitely. There are several ways to achieve the same thing in NumPy. So even just to count the unique classes, you can use different other functions also. Okay. All right. So now we have to plot this. How do we plot this data? We actually did it yesterday also. We want the first feature on the x-axis and the second feature on y-axis. So matplotlib we have already imported. So plt dot plot we can use.
X of 0, X of.
X of, we want all zeros, sorry, all rows and 0th column on the x-axis. And we want all rows and first column on the y-axis. Okay. And let's say I want it in plt.plot I'm using instead of plt.scatter. So I might need to pass what marker I want. So this is the kind of data there is, but I want to plot this data in such a way that the data points which belong to class 1, they should be in one color, and the data points which belong to class -1, they should be in some other color, right? So what I can do is, this is all the data points, right? This is the first feature value for all the data points. Now I can further declare that I want only those of them where y is equal to -1. Okay. Similarly, I can have one more statement where y is equal to +1. Okay. I need to do the same for the y-axis as well. Okay. Here once again I'll write, I am interested only in those data points where y is equal to 1 here. So what I did here, I want the data points belonging to one class to be in one color, the other class to be in another color. So I will pass two plt.plots here. The first class, let's say I represent in red color, and the second class, let's say I represent in blue color. Now, how do I extract the data points which belong to a particular class? This is going to give me all the first, all rows and first feature for all the data points. I am mentioning that I'm only interested in those data points where y is equal to -1. So these two places, I'll just add this thing and let's see. So these are the data points where y is equal to -1 and they are shown in red, and these are the data points where y is 1 and they are blue. Okay, is this clear? Any
What
doubt
is
so far?
O stands for?
O stands for dot. So you can have multiple markers here. Let's see. So these are stars here, and similarly, let's say capital D is for diamond, I guess. There's capital D and small d. There are several markers you can look up. Yeah, so this is a diamond. So several markers you can pass here. First thing is the color. Second thing is the marker shape. Okay.
Excuse me, ma'am.
Yeah.
How we are writing that x and y together? Because x is the different matrix and y is a different one.
Okay.
But in the plot you are writing.
Okay. So when you write y double equal 1, what do you get?
Boolean.
Boolean. An array of Boolean, right?
Yeah, yeah.
An array of Boolean. So now what is this? X, what is this part? Let me copy paste and let me show it to you. What will it give you? It will give you an array, right?
Yeah,
It's
first
an
feature.
array, right? Now this is an array. Replace this by some number, some letter. Let's say A. Okay.
Okay.
You have done this before. In some numpy array, in the brackets, when you pass a Boolean array, then what happens? Only those values which, wherever there is true, those values you get, right? We have
Yeah.
done this. So
Yes.
this is just simply one array. Now inside this, in the subscript, we are passing a Boolean array. That's all we are doing.
Yeah, yeah.
Okay.
Okay. Yeah, got it. Yeah.
Got it?
Thank you. Yeah.
Yeah, that's what we are doing here. So might be good to practice this. This might be quite useful. Okay. Now let's move on to implement Perceptron on this kind of data. We'll start with a 0 vector to be the initial W vector. So I'll write W is equal to, we know numpy dot zeros, right? Numpy dot zeros can create a numpy array containing all zeros. Now what should be the shape of this vector? Can somebody tell me?
X dot shape 0.
Is this correct, everyone?
0, 0.
Is this correct?
No, ma'am,
Everyone?
it should be
Shape of
1.
1.
It should be
Ma'am,
1?
One
number
separable.
of columns.
It should be 1?
Yeah.
Yes, 1.
Teacher should, ma'am.
So what is the shape of weight vector? It is equal to the number of features, yes?
Yes.
Yeah.
Right? It is equal to D, where D is the number of features. It is not equal to N, where N is the number of samples, right? So that's why we'll write X dot shape of 1. Here in this case, there are two features. So you are going to get only two values. This is our initial weight vector, right? Now,
I think, ma'am, we also need to add one feature, right, for the dummy feature.
yeah,
Because
if you want that the decision boundary does not necessarily pass through the origin, then you can pass on an intercept, a bias value. Okay.
yeah, in this example, it that doesn't pass through the origin, right?
Let's see. In this case, yeah, let's see. I
Okay.
don't know. Let's see without that, and then we'll see. Okay. All right. So this is the weight vector that we will proceed with. Now, what is the next step? As you have seen, after initializing, what's the next step? We have to pick a data point from the data set, and we have to check whether the sign matches with the target or not. Right? That's what we have to do. So we will pick the data points from the matrix X one by one in the same sequence in which they are present. That's the sequence that we are going to follow. For each data point, what are we going to do? We'll compute W transpose X, right? That's what we have to do. And we'll see whether it is, if it is greater than or equal to 0 in case of positive class, there is no error. If it is vice versa, then there's an error, right? So let's start off. So I'll do one thing. I'll proceed with the same thing. I'll start the for loop here. I'll iterate over all the data points in X. So what should I write here? Anyone?
X dot shape 0.
X dot shape 0, very good. We can either write that X dot shape 0, or we can also write length of X. What does length of X give you?
Number of rows.
Number of rows, very good, right? Length of X is going to give us number of rows. You can write shape also. Now for each data point, how do I access the first data point? By this? Yeah, this is your X. Where is your X? This is your X, right? If you have to access the first data point, how do you access it? X0, right? If you have to access the second data point, you write X1 and so on. So to access the ith data point, you write Xi. Now, you have to compute W transpose X for this data point. So what should I write? Is this correct?
W
At the rate. Very good. So whenever there is a matrix multiplication, we have to write at the rate. So W transpose Xi, this is what we have to find out. Okay. So what I will write is, I'll have some variable, let's say ypred, which will keep the predicted value of y. So I'll write ypred is equal to 1 if W transpose Xi is greater than equal to 0, else minus 1. Is this part clear to everyone?
Ma'am, as W is a vector only, so directly W should work also. No?
Directly W. What is the shape of W? What is the shape of W?
2 cross 1.
2 comma, right?
2 comma, yes.
2 comma, right? What is the shape of Xi?
50 cross 2.
Sorry, X1, let me say, and let me write, let's say.
1 cross 2.
Oh, 2.
Both are 2 comma, right? If you have to multiply them, can you do it simply without any transpose? No, right? You have to
Actually,
transpose, right?
yes, but there is no concept of transpose in the vector.
Yeah, I think
heard
without
in some
transpose
of
also
the.
it will work.
So what is happening here? W is this, and so we are actually by writing at the rate, we are taking matrix multiplication, right? We are doing the
Yes.
matrix multiplication by writing at the rate, and whenever we do matrix multiplication, then rules of matrix multiplication should be followed, right? So if
Okay.
this
So,
is the
so
kind
this
of
is
vector,
to avoid the
you convert it.
confusion.
Yeah, obviously. So you convert it to be of this type, so that you multiply them like this, simply how you do matrix multiplication.
Okay.
Because you're using at the rate.
Because the vector dot transpose give the same vector.
Yeah, you could use dot also, correct. You could use dot dot, right? You could
Yeah,
use
NP
dot
NP dot. Yeah.
np dot, correct. Yeah, you could use that also. But this seems, I think, more readable in general. Anyway,
Yes.
whatever works with you, you can use that. So what I'm doing here, if this is greater than equal to 0, now obviously the predicted class will be 1. Okay. If W transpose X is less than 0, then the predicted class will be minus 1. So you can write if else separately, or you can club them together like this. It's up to you, doesn't matter. Let me print the Y actual value. Where would be the actual value of Y? Yi, right? And let me also print the predicted value. Okay. So I'm going to print the actual and predicted value for each data point. Let's see what we get. So this is what we get. So this is matching here, matching. It's matching here. It didn't match here, right? It didn't match here, like that. It didn't match here, and so on. So this is how it is going on, right? Any doubts so far? Okay. So if this is clear up to now, what is the next step? Now we have found the predicted value of y. Okay. Now, what is the next step? We need to check whether it matches with the actual value or not, right? If it matches, what do? We don't do anything, right? If it matches, we don't do anything. And if it doesn't match, then we apply this update rule, right? So that's what we have to do now. Let's see the next part of the question. If prediction doesn't match the actual class label, update the weight vector using this equation. Okay, I'm copying this code and we'll continue with this. So what do we have to do? We have to compare yi and y pred. Not only that, we also have to keep track of what kind of mistake is happening, right? So I told you, if the mistake is like this will be the weight vector. If the mistake is like this will be the weight vector. So when will the mistake happen? When actual y is +1 and y pred is -1, right? This is first kind of mistake. The other kind of mistake is when actual y is -1 and y pred is +1, right? This is the other kind of mistake. Please mute if you're not speaking to me. Okay.
Madam, we can just multiply with y, no? Then we don't need two cases.
Multiply with y. You can multiply with y, but you need to check which kind of mistake that is happening, right? So what you're saying is you can simply write wt plus 1 is equal to wt plus xy, right? So yeah, so whenever there is mistake, which means whenever there is a mismatch, you multiply with y. Yes, you can do that also. So you're trying to club two statements, you can do that also. Yeah. So first you have to check whether there is any mistake that is happening or not. If there is a mistake, then you multiply it with y. You can do that. And so this is just checking the two different kinds of mistakes. So we are doing it separately. You can do together also. One and same thing. Please mute if you are not speaking to me. Okay. So okay. So if yi is equal to 1 and can you please okay. Okay, if y is equal to 1 and y pred is equal to -1, so let's say you want to keep track of how many kinds of mistake 1 and mistake 2 are happening, you might want to do it separately. But if you're only interested in how many total mistakes happen, doesn't matter which type, then you can simply use that formula. Okay, so w is equal to w plus xi. This is the first mistake that we are handling. Yeah, so somebody was asking this, so you can simply write yi into xi here. Okay, you can do that also. All right, if let me copy paste. If yi is equal to -1 and y pred is equal to +1, this is the mistake 2. If you want to keep track of that, you can write them separately. So w is equal to w minus xi. Okay, so we are applying the weight update rule, and now once again we are printing the actual y and predicted y. Okay, so we are writing in the same for loop, and this is what we are getting. So you see that there's a mistake that happened here, and since the mistake happened, then the weight update rule was applied, and after that in the next one there was no mistake. In the next one there was a mistake, and then hence the update rule would have been applied, and subsequently there was no mistake, and so on and so forth. So this is the effect of applying the update rule. So let's keep track of how many mistakes happened and how much would be the loss. So in the same code, keep track of the total number of mistakes made by the algorithm. So let's now create a variable so that we can keep track of the number of mistakes. I'll copy paste this code and I will update this only. I'll create a variable, let's say total mistakes, initialized to 0. Whenever a mistake happens, we apply the update rule. So, okay, so here I can increment the total mistakes that happened. Total mistakes plus equal to 1. And here also, I'll write total mistakes to be incremented by 1. Okay. At the end of this for loop, we would have known how many total mistakes that happened. So let me print that out here. Okay, let me execute this. So total mistakes that happened in this particular data
But
was only
ma'am, in this case, wouldn't the W will be the latest to last mistake? It should be first mistake, right?
W. So by the end of this for loop, whatever W we will get, will whatever is the latest value of W, that will be the final W.
But we take the first mistake as the new W, right? Not the last W.
We should put two for loops, no, madam, because after correcting the W, we have to again iterate all the values
Yeah,
of
we are going
X.
to do that. We are going to do that. Okay. So for
So
now, we have only iterated over the data only once. Okay. We are going to repeat this process, which we'll do in the next step. Uh, Getting back to somebody had a question. Can you repeat your question? The latest W and all.
Ma'am, when the loop runs, right? So total here are two mistakes. So new W is always at the point where we had the first mistake, right?
No, not the first mistake. So let's say these are the data points, and we are running the for loop, which will be iterating over the data points once. So tell me now. So we started with W to be 0, and we evaluate it here. Now go on. What's your question now? Hello?
Yeah, I think he's saying that if W0 is giving mistakes means for two data points, say x3 and x5, there
We
are
are
two
not going to
mistakes.
check x3 and x5 together on this W. Please note. That's what I've been repeating. You will.
Okay, so that number of mistakes which is coming to 2, so how to interpret that? Means what is
Yeah, so this means that in one pass through this data, only 2 mistakes happened, and hence 2 weight updates happened. Okay, that's what it means.
Ma'am, the problem is
keeping the W updated, we have got 2 times mistakes.
Yes, keeping the W
suppose we
updated. Yeah, go on.
That is in the same pass, right? We have to like complete the pass with new W, right?
Okay, let me give you an example. We start with this copy of W. You apply on W on X1 by computing W transpose X1. Let's say it matches. If it matches, what do we do? Tell me. Tell me. You
We
move
don't
to
do
the
anything.
next data
We
point.
move to next.
We don't change
Yeah, we
anything.
move
Next
to
data
next
point with W naught. Let me put W naught here. This is initial, right? W naught. The first copy this is. Now we evaluate W naught on X2, right? And we check whether there is any mistake or not. Let's say there is no mistake. What do we do? Tell me.
Move
Tell
to
me.
next data point.
Move to the next data point with the same copy. Now let's say there is a mistake here. Let's say there is a mistake. Let me write M. There's a mistake here. You update this W naught to, let's say, W1. Okay. Now with this W1, you do not evaluate the next data point with W naught. You evaluate the next data point X4 using W1. Is this clear? Now.
Yeah, so this is clear, ma'am. So let's say now we got W1, right?
Sorry, one by one.
So now we got W1. So with this we have to complete the iteration till end, right? Like
Let
say
me finish.
till
Okay, let me finish. So with this W1, you evaluate X4. Okay. Let's say there is no mistake. You move here with W1. Okay. you evaluate x5 with w1. Let's say there is no mistake. Let's say you move to x6 with the same copy of w. Now let's say there is a mistake. Let's say w1 is not able to correctly predict x6, so there is a mistake. Now you will update w1 to w2. Okay, now one pass over the data is over, and we had we had encountered two mistakes, and consequently we updated w twice. So total mistakes in this case is 2. This is what is going on. Now go on, please, one by one. Now what is the doubt?
So we are going to have another pass now on the data,
Yes,
right?
we will do that. We will do that. So far, this particular for loop runs through the data only once. We are going to have another more iterations over the data. Is that clear? We are going to code that.
Okay, ma'am. So in final loop, there will be no mistakes actually.
Yes, correct.
Any number of mistakes.
Yeah. So let's finish the next step, and then maybe if there is still any question, you can ask. Yeah. So far, we have run only one iteration over the data. Okay. Run the same for 10 iterations, but stop if there are no weight updates in an iteration epoch 1 and same thing. So you can fix this value actually. Given the data, you can just, this is a parameter that you pass before you start. So let's say we are going to try for 10 iterations. Okay. So this whole thing we have to do 10 times now, which means we have to put this in another loop. So let me copy paste this and we'll make changes here. Okay. We have to run it for 10 iterations. So let me create a variable for that. Let's say, let me have epochs is equal to, epochs is equal to 10. We're going to run it for 10 epochs. I'm going to put this entire for loop inside another for loop because we need to have several passes over the data. So I'll write for epoch in range epochs. I hope this part is straightforward, right? We're just going to run the following for 10 times. Range epochs starting from 0 to 9. Okay. Let me also print which epoch we are in right now. So I'm going to just print which epoch we are in currently. Okay, this will just print the iteration number. Let me also keep track of one more thing. What I want to do is, so what we are saying is stop if there are no weight updates in an epoch. Okay, so here in the first epoch, there were 2 weight updates. Now there is this W2, right? With this W2, we go once again to X1. Okay, with this W2, we go back to X1. Once again, we repeat the same process. Let's say the number of mistakes that happened in this pass are 1. Okay. And then we move with the latest copy of W to the next epoch, third iteration. Let's say there was no mistake in this case, right? There was no mistake here. And that's what we are saying. If there are no weight updates in an epoch, so here we see that there were no weight updates, we can actually stop. We were actually starting from 1 up to 10 iterations. We started off that we will execute 10 iterations, but there is no point continuing after an iteration where there were 0 weight updates, right? Which means we have already found a W which is able to classify the data point. So we can stop there. Okay.
Ma'am, it could also happen that the number of mistakes may increase in next epoch.
The number of mistakes,
it may increase also for some iterations, for some epochs.
So
or
it
will
may
always
happen.
it will always decrease and go to 0.
So it actually reduces. So if the data is not linearly separable, it will actually fluctuate. Okay, it will go up, it will go down, it will keep fluctuating. I will show you that case also in the code. But if the data is linearly separable, it will reduce. Okay.
Yeah,
Ma'am,
yeah,
you are
yeah.
not specifying any margin here, right? So data is linearly separable, but there is not necessarily be a margin, right? So if we are updating the W, then that updated W might incorrectly classify the previous data points x1, x2, x3, right? When we are updating W, like for when we correctly classify x3, suppose, then we update the W. Then that updated W might incorrectly classify that x1 and x2, right? So in that case, in the next iteration, mistakes will be much higher.
Okay.
Like previous one.
Okay. Firstly, whenever we make an update, so if you have studied the update rule of Perceptron, W new is equal to W old plus XY. If you study this, why does this help? Why are we so somebody told us, okay, you do this, you just add to the old weight vector, you just add XY. Now, how do we convince ourselves that this is going to work? This is going to help us to reduce the errors. So there's a particular analysis of this update rule. If you want, we can cover that. I explicitly skipped that in order to focus on code. So one thing that you can understand about the update rule is that the update rule always tries to move the weight vector W to the right direction. So there are two kinds of mistakes, right? When y is equal to +1 and when y is equal to -1, there are two kinds of mistakes that happen. You can study each of these kinds of mistakes, and we will see that in each case, W moves to the right direction, which means if W was already, predicting -1 for some data point, we alter W such that it now moves towards the positive side. So it moves to the right direction. Similarly, if if W was already predicting, let's say, +1 for a data point where -1 should have been given, then we update W in such a way by using this update rule that this prediction moves to the negative side of it, so that it tries to match this. So that's the beauty of this update rule, that it takes the weight vector to the right direction, whatever be the right direction, based on whatever kind of mistake that happened. So, and second thing, the proof says that the number of mistakes is going to reduce only, and there's a limit how many mistakes that can happen by the perceptron algorithm. Okay. And getting back to somebody was asking about margin, so I explicitly gave this class separator to be 3. This makes sure that there is going to be a good margin between the data points. If you reduce it, then obviously this margin is going to reduce. So I arbitrarily gave a decent value here. I don't know what is the default value. Maybe we can check that. So yeah, the default value is 1. So I explicitly increase this value to make sure that the data that we get will be having a good margin. There's a good gamma margin there. Okay, so yeah, that will take care of the part that there's a gamma margin here. Okay, now any more questions before we proceed?
Here
Yeah.
we have two features, so it is very easy to visualize also, and
Yeah.
that it is linearly separable or not. But once we go in the higher dimensions, so what are the options that to know whether it is linearly separable or not?
Okay, so you want to check that computationally, is it?
Yeah, ma'am. Just by implementing the models and getting accuracy is the one of the method which I find.
Yeah, that's one way, correct. So if you apply perceptron there, and if it is converging, that's one indication that the data was linearly separable. Okay.
Yeah, and is there any other way also
to check whether the data is linearly separable, is it? So,
yeah.
So okay, generally speaking, when is the data linearly separable? When you're able to find W such that, you're able to find some W such that there's a linear separator W transpose X, which is able to tell for each data point correctly. Whenever this is greater than equal to 0, the class is predicted to be positive. Whenever it is less than 0, the class is predicted to be negative. When this is happening, then you can say that the data is linearly separable. Now, if the data is in 3D, let's say, if you are able to get some W such that you get a plane, which is a linear plane, which is able to divide the data correctly, then you will say that it is linearly separable. Now, how do we get this W? Okay, so obviously, like we discussed, the one way is to apply perceptron algorithm, and that will give you W, right? So I can't think of any other quick way to tell whether the data will be linearly separable or not. Quickly,
Ma'am, can
I
you
don't.
use the PCA algorithm to check? I mean,
How would PCA help here?
it will reduce the dimension to like lower dimension, and then we
Project in the
can.
other dimension, no?
Yeah, I think
Okay,
in the
let's say there is a 50 dimension data, and you will project it to 2-dimensional space, is it?
yeah.
Okay, there's some loss that happens there. If you're okay with ignoring that part, then some quick idea you can get, but I don't think that may be accurate. Quickly you can get some idea. Depends on how many dimensions you are reducing to 2, right?
Yeah.
So, but there'll be some noise that will come up there. If you're okay ignoring that noise, yes, you can get some idea
Yeah.
about separability. Yes. Okay.
Okay. Yeah.
All right.
Ma'am,
So,
directly perceptron we use in real life scenario? No, right? This is just a basis of algorithm, right?
no, we actually use in sklearn also perceptron is there, and we apply to different algorithms and different data sets. Um, so in perceptron, in general, we give some limit on the number of iterations, like what we are going to do also here, number
Yeah.
of epochs. Okay, so whatever result we get there, there'll be some mistakes even with the final W we will get after stopping after some number of iterations, but we are okay with that because real world data is never linearly separable, right? And we never get 100% accuracy, and we are not looking for that also in real world data, right? So we
Correct.
actually use perceptron algorithm in practice. Let's say sklearn also has it, and we do use it on along with other algorithms. This is also used. Okay. All right. So yeah, where were we? Run. Yeah, I was telling you, let's keep a track of how many mistakes happen in each epoch, so that whenever there's zero mistake that happened in a particular epoch, we stop there. So for that purpose, I'm going to have a dictionary. I hope everybody is comfortable with dictionaries. So weight updates per epoch is what I'll do. And I'll create a dictionary so that I can have key value pairs. You can use any data structure that is comfortable, but I find dictionary is comfortable here. So the key will be the epoch number. Epoch number, let's say first they are starting from 0, right? So 0th iteration. So the iterations will go from 0 to 9. Okay. 0th iteration, let's say 2 mistakes. First iteration, let's say 1 mistake that happened. Second iteration, let's say 0 mistakes. This is what I want to keep track. Keys are iteration numbers, epoch numbers. Values are number of mistakes that happen. Okay. So how do we do that? So I've started this.
Can we use also the break? I mean, there is some loop
Yeah.
break.
Yeah, definitely. We can use break to come out of the loop, but for break you need to check a condition, right? What condition you will check?
That
Whether the
number of
number of
mistakes is
mistakes
equal
that
to 0. Yeah.
0 or not, right?
Yeah.
So apart from that, I also want to record this detail. What detail? How many mistakes happen in each epoch? So I'm creating this structure.
Okay.
All right. So for epoch in range epochs are 10. So it will go from 0 to 9. I am printing which iteration we are in, and I'm initializing this value. Weight updates per epoch is equal to, per epoch for this epoch. I hope everybody knows how to add some key value pairs to a dictionary. This is how we do it. Dictionary name, and then in the brackets you write the key and equal to value. Then epoch colon 0, that key value pair will be added. This key value pair will be added to the dictionary. Okay, I hope that you remember. Now all this should happen inside this. So I'll put an indentation here. Yeah. So I've just put that for loop inside this. What other change I should make? Let me comment this. We don't want to print this. So yeah, whenever a mistake happens, I want this to be updated as well, right? Weight updates per epoch for this epoch should be incremented by 1 plus equal to 1. Right? So I'm having two variables. One is for total mistakes, okay, and the other for mistakes that happen in each epoch. So I'm keeping track of both these things, and we'll print that, and that'll give us extra information about how this perceptron algorithm ran. Now, after this is over, after this for loop is over, which means we have iterated over the data 10 times. Okay, let's print these values. Let's print this weight updates.
So, ma'am, this weight update per epoch could be 0 also for, say, epoch number 4 or 5.
Yes, definitely.
Yeah, so it will not break there. No? It will break only after 10 loops.
Yeah, I'm going to add that. So what I have to do is, we are still in the for loop here. We are inside the for loop. So I should add here, if weight updates per epoch for this particular iteration, for this particular epoch is equal to 0, I want to not proceed further. I want to come out of the for loop. Okay, so this extra thing I am adding. You can actually leave this. Will print it later on. Okay, so this for loop, this is one iteration complete. This is one iteration complete. Okay, and after this first iteration, we have how many weight updates that took place in this particular epoch, and if that comes out to be 0, we want to not proceed with the next epoch. Okay, so we are breaking here. Okay, total mistakes we are printing. Let me also print the value of this dictionary, which is all the updates that took place in each epoch. So this is what I'm printing. Let me also print the latest value of W, which is the W that was the last one. Okay, this is what we are getting. So this epoch number we were printing initially, so that's what we are getting, epoch 0, and then epoch 1, and then total mistake that happened 2, and this is the dictionary that we are printing, which means in 0th iteration 2 mistakes happened. In the first iteration 0 mistakes happened, so it came out of the for loop and it stopped. And this is the final W value, weight vector value. Okay, is this clear to everyone, this part? Any doubts in this? So I've simply created a dictionary here to keep track of how many mistakes are happening in each epoch. Okay, weight updates per epoch, for a given epoch I initialize to 0, and whenever a mistake happens, I not only increase the total mistakes variable, I also increase the value corresponding to that particular epoch in the dictionary. So that's what I'm doing. And once an iteration gets over, which is this one, I'm checking how many mistakes happened in that particular epoch. If that is 0, I come out of the for loop. So although we started off with 10 epochs, there was no need to perform 10 epochs on this data. Within just after one iteration, we were able to Perceptron. So if the data is linearly separable, Perceptron actually works very well and quite fast. It's quite fast if the data is linearly separable. As you can see, in one iteration, it was able to manage. And this W is the final weight vector, which we got at the end of the first iteration. This one probably. Okay, 2 mistakes happened, one here and second here, and after that there was no mistake. So this is the final weight vector value which this perceptron is returning us. Okay. Any doubt so far before we proceed?
Ma'am, here we have set a number of epochs to the 10. So is there any thumb rule to set this number of epoch, or it will depend on the number of rows in the data set, or like
It
that?
actually, there's no thumb rule actually. In practice, we try out different values. So this is one of the hyperparameters. If you know what are hyperparameters, is something that
Yeah.
have to be provided by the user before the algorithm starts, right? Like k,
Okay.
k value and k mean. So we try out different values of k there, right? Here also, given a data set, so given seeing the number of rows in the data set, you may not be able to tell because we don't know how complicated that data is, right? So there is no rule of thumb actually. You try out different iterations and you see whether you see any improvement or not in the loss. Yeah. Okay.
Thank you, ma'am.
Yeah. Any other questions? All right, let's proceed. Plot the weight vector and the decision boundary. Okay, let's try to plot things now. I'll copy paste that code and we'll make changes in there. This is the data that we had. Okay. Okay, we want to plot the weight vector W, right? So generally that is, plotted like this, like a vector. In matplotlib, in order to plot a vector, we have something called quiver, which probably we can use. There could be several other ways you can explore. This is one way that we can use to plot a vector which has an arrow. So quiver is what we'll be using. First two parameters are where the vector will begin. So I'll pass 0, 0 there. The second two parameters are the direction of the vector, which are given by W itself, right? So I'll write W0, W1 here. Okay. Now, these values of W are not huge, so it will plot a very small weight vector. So I can make use of a parameter scale. I'll give some value, some arbitrary value I'm passing. You can try out different values to scale this. And I'm also giving a particular color for this vector. Let's see what we get. This is what we are getting. Okay. Now let us also plot the decision boundary. Now the decision boundary is perpendicular to the weight vector, right? Perpendicular to the weight vector. Now for a given vector, how do we get a vector that is perpendicular to it? Anyone has any idea? Let's say there is a vector and it has two components. Let's say
multiplication with
Multiply with -1.
Multiply by -1, is it?
Yes.
Dot product should be 0, right? So there's a transformation that you can apply. So if you want to get the perpendicular vector to A, you can multiply with a transformation matrix. This is a transformation matrix. So if this is a weight vector, if this is some vector, if you want to get the perpendicular vector to it, there'll be two vectors actually. One is in anti-clockwise direction and the other which is in clockwise direction, right? There are two vectors which are perpendicular to any given vector. In order to get this kind of vector, which is anti-clockwise, you can multiply with this transformation matrix, the vector A, you can multiply with this matrix, and the result will be this. Or if you don't want to get into all this detail, you simply should know that if you want to convert Ax, Ay to vector which is perpendicular, you replace Ay and Ax and you negate the first one. So this will be your first perpendicular vector. And the second perpendicular vector, this one, you can get by simply negating the signs. That will be ay minus ax. So these two we can plot here. So here in this case, what we have to do is the vector is there and we have to draw its decision boundary. So this is a workaround that I am using. If there is any other way, you can go with that also. So I am simply using once again PLT dot quiver 2 times in order to have the perpendicular decision boundary. If there is any other way, you can proceed with that also. So given W0, W1, its one side of perpendicular vector will be minus W1 and W0, right? Once again, we can have some scale, just keeping some value. Let me have some color. I don't want an arrow here, right? In quiver, by default, you get this arrow, right? We don't want arrow, so I will mention the same by using some more parameters. You can check out the documentation of quiver whenever needed. So head axis length is some parameter. I don't want it. This is to suppress this. This is just a workaround to suppress this arrow. And head length also 0. This is what I'll have in both sides. The second side will have the signs negated. And scale is this. Yeah, so this is 1. I can still increase the size. So there's one more thing that you can use. You can. So this is not visible nice enough. So you can increase the limit of this y-axis by using plt.ylim. I don't know whether you came across it earlier or not. Some values I'll pass. Let's say these values I'll pass. Okay, and so you can explicitly mention how the limit of the y-axis. You can do that for x-axis also by using plt.xlim. That also you can use. And let's show the grid also. Okay, so this is the kind of decision boundary that we are getting. Simply we plotted the weight vector and we plotted a perpendicular line. This actually is a workaround. You can check out other options. And we see that this decision boundary is able to perfectly classify the given data points, given that they were linearly separable. If you compute the loss of perceptron on this given data, how much that will come out to be? Anyone?
0.
0, right? Because it is able to perfectly classify. We can cross check that also. So I'm having one variable, loss initialized to 0. How do I compute the loss? Can anybody tell me?
0, 1 loss.
Yeah, how do we do that?
Y
Of the
calculator.
predicted y.
Yeah, we have a final y. Y is it? No, we have w, right? We have this w weight vector, which is the final weight vector, which you can see here as well. So what we are going to do is we'll apply this weight vector on each of the data points. Okay, and if the sign is matching, if the y pred is equal to actual y, then loss is 0. If it is not equal, then the loss is going to be 1. That's the logic that we have to use. So we need to iterate over all the data points, right? So I'll iterate over all the data points once again like this. Okay. I can actually copy paste that code that we had written earlier. Y pred is equal to 1 if W transpose X I is greater than equal to 0, else minus 1 is the same thing. Right, so we got y pred now, and now we have to compare this y pred with the actual y value, and the actual y value is where? Yi, right? So if you can simply write if yi is not equal to y pred, loss plus is equal to 1. Or you can also do it separately by giving cases of types of mistakes, but that's not needed. So I'll simply write if yi is not equal to, if yi is not equal to y pred, I need to increment the loss, right? Is this clear? Is this correct so far?
Yes, ma'am.
Okay, so whenever there's a mismatch, I increment the loss. So let's see what do we get here. Since we know that there is no mismatch and our weight vector is completely able to classify well, so loss is going to be 0, right? So this was the perceptron algorithm applied on a linearly separable data. Any doubt in whatever we did so far?
Ma'am, in that quiver decision boundary we drew, right?
Yeah.
So
Yes.
in the decision boundary, how can we say that it is always starts from 0, 0? Because if the intercept is there, so in that
Yeah,
case, how do we draw the decision boundary?
Yeah, so in that case, you will not write 0, 0 here. You will write whatever the value of intercept is there, right? So if you don't want, so far in this particular case, we considered that the weight vector should pass from 0, 0 origin. But if you want to make it a little more generalized, that the decision boundary may pass from anywhere, then you will pass a bias value. You will pass a dummy feature in the given data. You will modify the given data.
Yes.
So you'll add a vector which contains all ones, and subsequently you will have a weight vector which will have 3 parameters. Here
Okay,
the
so
weight
that
vector had here the weight vector had 3 values, right? Sorry, 2 values, right? In that case, weight vector will have 3 values. Okay, and the first value will pertain to the intercept.
Okay, got it. Thank you.
In the plot, where was the direction of the weight vector coded in?
Yeah, this one. This one.
Okay.
Yeah. Okay, any other doubt so far? After this, we'll move on to non-linearly separable case. Actually, we have written the code. We'll just apply it to a non-linearly separable data. Okay, so assuming it is clear, let's move on. Now, I'm using the same statement to create the data set with just one change. The flip y value, which we were earlier passing 0, which means fraction of data points which will be randomly assigned the class will be 0, which is what we were passing earlier. Now I'm going to pass 0.1, which means 0.1 fraction of data points will be randomly assigned the class. So there is likely to be a noise in this kind of data. Let's execute this. So we need to plot it to be able to see how or whether it is noisy or not. This is X that got generated. I'll copy paste the code to plot it. And let's also replace these things, 0 by -1. Let's do that also. We'll apply the same code again. And we'll see how Perceptron behaves on a non-linearly separable data. Okay. Okay, so this is the kind of data that got generated. As you can see, there are noisy points here, and hence the data is not linearly separable, right? Now, what happens if we apply the Perceptron algorithm on this data? Let's see. So I'll copy paste this code that we have written for Perceptron. And let's see how in different iterations Yeah, so this is, I don't think we need to make any change here. Everything should be fine. Yeah, let's execute. Okay, so this is what is happening. We started, we mentioned it should check for 10 iterations. So all the 10 iterations got executed because it was not able to converge. Now total mistakes is this much. And let's see this dictionary. In 0th iteration, 13 mistakes happened. In first iteration, 11 mistakes. In second iteration, 12 mistakes, and so on. So 11, 11, 10, 11, 11, and so on. It is not going to reduce because it is not possible given the way perceptron algorithm works. On a non-linearly separable data, it is going to oscillate. Kind of the decision boundary is going to oscillate left and right and so on. And this is the latest weight vector that we had. Okay. So this is how perceptron behaves on a non-linearly separable data. Any doubt in this?
So, ma'am, I was wondering means how this support vector machine means soft margin support vector machine will work. Means it will actually separate. No, it will not separate. But there will be some
penalty.
Penalty.
Hmm.
So
yeah, so this technique is different. SVM is completely different. So the way SVM works is there's some penalty that gets added if there is a data point which is on the wrong side of it, right? So obviously there'll be error due to the due to the data points which are on the wrong side. It's not that SVM will also be able to completely separate the data, which is something like this. It's just that it works in a different manner. Here also, so there'll be some error in SVM also, and there'll be some error here also. You can actually proceed with this.
Like yes, that's what I wanted to say that.
Yeah.
Yeah, with some loss, we can proceed.
You can proceed, definitely. It's just that you cannot expect a zero loss there. That's all. Okay.
And loss is not means loss will not be the zero there also.
Loss will not be zero there also. There'll be a penalty that is being applied. There also will get a loss. If you get a lesser loss here, you can actually proceed with a perceptron. Okay.
Yes.
Okay. All right. Any other questions in perceptron? So this was actually not a very complicated one. So yeah, this is the most basic implementation of perceptron. So you can try out further things on this. You can try out different kinds of data sets and see how your perceptron behaves there. So this was all. If there is any doubt, we can take. Otherwise, that is done.
It's a generic doubt. We have a perceptron in sklearn library also, right? And do we have many algorithms in sklearn also? So how far should we learn this coding,
this coding from scratch,
logic?
Is it?
Yeah.
See, you should be able to write code from scratch. You should have this capability. Okay. There are libraries for everything. For all these techniques, there are libraries. Probably you might just be, if you're working somewhere later on, you might just be using these libraries. It actually depends on the role that you'll be working on later on, right? Let's say you're going to work as a data scientist. So there are several roles, right? Data engineer, data analyst, data scientist. If somebody wants to get into research, let's say, this is one use case that I'm telling you. So so what do researchers do? They might want to come up with new techniques. If you want to come up with a new technique, so this perceptron somebody developed, right? Other researchers are still working on developing new techniques. If you want to get into that particular direction, you should obviously be able to code from scratch these techniques. Only then you will have the capability to come up with a new technique from yourself. So that's why it gives you a better understanding of how these techniques work. So it actually depends on what kind of role you're working on later on, right?
Okay.
Does it make sense?
Okay, got it. Yeah. Thank you. Thanks a lot.
Okay.
Ma'am?
Yeah.
In this first, when you generated a data set, okay, what this class separator do? Like
Yeah,
I
class
just want.
separator, this is okay. Let me show you the detail. Is this? Yeah, the factor multiplying the hypercube size. So default it is 1.0. Larger values spread out the clusters and make the classification task easier. So by default, the value is 1. So you can try out different values of this class separator. So internally, whatever equation they use, I will have to check that out. But let me try reducing this value to experiment. So I kept it to be 1. Now you would see that the data, there'll be lesser gap in the between the data points. I'll have to run this. And let's visualize it. So you see, the data is actually kind of intermixing. It's actually not linearly separable now, right? So in
Yes.
order to make sure that they are far apart, I had given this value of 3. Let's see what we get by 2. So there's some, as they're mentioning, they are using some particular equation to which takes in this value of separator that we are passing, that we'll have to explore in the source code. So this is also linearly separable. So if you want to increase the gap, then you can increase this separator. Okay.
And this in informative, like.
Okay. Yeah. So I was telling you, in any real world data, some features are useless. Some features are just add noise. So we might want to get rid of them. Some features are redundant. For example, if there is a feature, there's a feature 1 which has some values. I'm taking a very simplistic case. There's another feature which has these values. Do you think it's a good idea to keep both the features in the data?
No.
Why?
Multiplication.
It's just F2 is just a redundant feature here, right? There's
Yes.
no new information that F2 is bringing in. So in real world data, there are some features like this. It may be the case. So this make classification that we are using, it provides you several possibilities to generate several kinds of data sets. If you want to generate a data which kind of resembles the real world data, you might want to probably introduce some features which are redundant as well, right? So here we didn't want that. So I gave redundant features to be 0. Okay. So by default, it is 2. By default, 2 redundant features it introduces. You can change this value. Is this
Ma'am,
clear?
it's same as like say we learned that row reduced echelon form which will reduce the data. So something similar might be happening.
Sorry, which I couldn't get you.
So we learned earlier in statistical maths, right? Row reduced echelon form which reduces.
No, echelon form.
Yeah. So it does it reduce the redundant?
Yeah, linearly dependent columns or rows you reduced, right?
Yes. Yes.
Similar. It is also similar. So there could be 2 cases here. If you're bringing in linear dependency, linearly dependent. So F1, F2 is just 2 into F1, right? There could be another case where F3 is there, where F3 is equal to F1 plus 2F2, let's say. Now F3 is dependent on both F1 and F2. So now this F3 is redundant. You might want to get rid of it. Okay. So it's actually similar. If you can whatever you're mentioning, that is the basics. So ultimately this is also going to be a matrix. Okay. And if you apply that row echelon form, then you will get reduced number of features.
Ma'am?
Yeah.
In real world, we will be provided with data, right? Like we don't need to generate this data.
Yeah. This is just an example.
Okay.
Yeah. I mean, this is just for the demonstration. We need to start with some data, right? You either use NumPy for that, which we did yesterday. You can actually use that code also to generate data for classification. Completely works. Or you can use any other way.
Ma'am.
One question, like say here all we do is like deal with some numbers, integers like that, but real world has strings and the other class type
Yeah,
as well. So
yeah.
their things are different, right?
Yeah, so we need to convert that textual data. I think you're referring to that kind of data.
Yes.
So textual
Right.
data has to be converted into numerical data. So that's what we do in NLP, right? For example, you're aware of bag of words, or there are several vectorizers. You might do it in MLP if you have not done that course yet. So there are several vectorizers. For example, count vectorizer, hashing vectorizer, TF IDF vectorizer. So they convert the textual data into a numerical format. Okay. So every word is actually a feature, roughly speaking, except the stop words. So you convert a given textual data into data which has numerical data. Okay. So before you apply all these models, you actually convert. So this is the kind of data that we dealt with today is also called structured data, and the textual data or image kind of data, that is unstructured data. If in order to apply any model, any technique that you have learned so far in ML, you need to convert that unstructured data to structured data. So I gave you an example how you convert textual data. There are several ways that exist. Okay, we will do that in any practical course on ML.
I have a question, ma'am.
Yeah.
Will we have more such workshops? Because this was really, really helpful. The way you explained. In fact, I want to thank you so much. All the sessions we had till now, the concepts were so clearly explained. I wish we had
Yeah, that was
had
the
this
motive.
earlier. I wish
Okay.
we had this earlier because I completed MLT, earlier during the year,
Okay. Okay.
and the coding was not explained the way you're explaining it. It's really, really helpful and has
Yeah, yeah.
cleared.
So that was the
But
motive. Yeah,
I
good that
wish
you
the other
discussed.
algos are also explained and you have more of these workshops so that we are at par with the current group, because they are. I think the current group is blessed to have,
Yeah, yeah,
gone.
you can say that actually. But
Yeah.
don't worry. I mean, yeah, we'll try to have more such workshops. So this is, I think, the first kind of workshop that we are existing. We are having here in this course. But we can plan more. So it was kind of a pilot run, which is coming out to be useful for you all, which indicates it served
It
its
was
purpose.
tremendously helpful. Yes.
Very nice to know that. So
It is
yeah,
very helpful.
we will plan such more such workshops. So definitely don't worry. So I think you might have access to the recordings of this session, just in case you
Yes,
finished MLT last time.
yes. In fact, I started looking at the recordings even since
Yeah.
yesterday, and they are way ahead of what we learned. I mean, they are so clear.
Okay. Yeah. So you can, so don't feel left out. You can actually continue watching those recordings,
Right.
just in case there's some algorithm which is not being covered as part of this workshop, just because of
Which
any
recording,
reason.
ma'am?
Live sessions, we have been taking live sessions, like in the previous the term that just got over. We took every week live sessions, having
Okay.
coding of all the concepts.
I
So
have one more request, ma'am. I believe there are some new sets of collabs also given to the people, the new current batch. But
okay.
we didn't have access to that. And if those collabs were made available to us, then the recordings would also be very helpful. In fact, we
Okay,
could
actually, at the
practice.
same the recordings are actually discussing those very collabs. But if you
Right.
want those collabs themselves, yeah, I think we can look into it. I've noted down
Right.
your comment, and let's see.
Madam,
We
even
can
in
actually make
current
it
batches,
available to you. Yeah.
Thank you.
madam, even in
Thank you.
current batches that collab, we are not able to open it now.
Whatever link I shared, were you able to open this?
Yeah, this we
Some
are
sort
able
of
to
project.
open it, but the term, the in the term, the which were given practical assignment solution collapse, we are not able to open it. The
Are you from the term that just got over?
yes, madam.
So what is okay? Okay. So the solution collabs will not be accessible to you because programming assignments that you have to submit as part of this workshop, they are, I mean, there's some intersection there, right? So you are not expected to be looking at those collabs. We might make them accessible after the deadline, which was set to be 21st of December. You have to submit the assignments, which will be used as a kind of eligibility criteria for the OPP. Okay.
What
After
is
that,
the
we'll make it
pattern of
accessible.
OPP?
Similar questions, whatever we are covering. If you do these sufficiently well, it should be fine.
Ma'am, for the assignments, do we just submit the answers or we have to submit the collab too?
Just the answers in the portal.
Assignments are already live,
will there be
right,
fees
ma'am,
for
on the website?
I'm sorry, I couldn't get you.
Assignments are already on the website. Today I got the mail, and there are
Yeah,
only questions
assignments
like
are there. They're accessible to you, right?
Ma'am, we are
yes,
not
ma'am. They're accessible. Ma'am, these videos won't be removed from the YouTube, right?
No, yeah,
these
these
workshop
videos will stay. Yeah, these videos will stay. Yeah, don't worry.
Okay, thank you.
Will there be any fees for the OPP?
That is being decided. Did you get any notification regarding that?
No, ma'am.
In the mail, it was mentioned that they will tell us what is the fees, or what are the charges for your OPP.
Yeah, so the fee will be intimated to you all. The amount will be conveyed. I may not be able to comment because it may not be finalized. So yeah, you will be informed about that. The OPP will take place after a few days, maybe in Jan. You will be intimated the details about that.
So, ma'am,
Ma'am,
OPP timings are fixed priorly.
I'm sorry?
Timings.
Timings?
OPP, yeah.
No, not yet. Not yet. They are yet to be decided.
But the date is, I guess, ma'am, fixed, right? I guess it is 14 January or 4th January. I'm not sure about, but I guess date is fixed. I'm not
It
sure
will
about
be
the
in
timing.
Jan, but date, if I'm not wrong, was yet to be
It will be
finalized.
somewhere after the term starts, around 24, 26 Jan.
No, it could be before that also.
But after the
could
term
be,
starts.
No, it could be before that
No.
also. You will be intimated soon about that.
The term is starting from 20, and I guess I'm not sure where I've seen, but there was somewhere it was mentioned that
It will be before that, most likely.
Yeah,
Most likely it will be
most
before the
likely.
term start. Yeah, not after.
Ma'am, one
Okay.
request. Can you please add me to this MLT workshop communication group? I'm not sure. I dropped couple of mail to support, but not getting added.
Can you drop a message at discourse? What about others? Have you been added to the group?
No, ma'am.
No, ma'am.
No group.
Because initially there were issues with G form, and then we're not able to get added.
Okay, maybe you can drop on this on discourse so that we can resolve it there. Okay.
Yeah. Yes, ma'am. Just we want.
So, ma'am, what is the next session about? What will be
Yeah,
there
next
about?
session is at 3, which is on SVM. Okay.
Excuse me, ma'am. I have a doubt in Perceptron. Small doubt.
Yeah. Go on.
Yeah, let's say we have a data set where only one data point is like not linearly separable. So because of that data point, the entire data set
Yes,
is
it will not give you zero loss. Perceptron will not be able to give zero.
It will give one loss, or like it can give more loss also. Like
loss will be one.
At the end of if we run the Perceptron algorithm, then it will give one loss.
Yes, yeah.
But in the Perceptron algorithm, what we have seen is like it fluctuates, right?
Yeah, but it will not converge. Even in the case that you're mentioning, it will not converge because it will keep making an attempt to handle that very data point, and hence it will keep trying shifting itself the decision boundary.
The loss will be the loss will be for that point or for other point.
So firstly, it depends on where you stop. Okay, where you stop. In none of the iterations, the loss, in none of the iterations, it is going to converge, but you're going to stop at some point. At whatever point you stop, whatever decision boundary there was, based on that, how many data points are on the wrong side, you'll get the loss. Okay. It may be the case that you stop at some point where the decision boundary is at a wrong place, and hence, because of one incorrect data point, others are also suffering. It may also happen. It may also happen.
Okay.
Yeah. Okay.
Hello, ma'am.
Yeah.
So if we scale the vector like with 100, then the length of the vector is small comparatively when we give the scale to 20 or 30. Why is that so?
You're talking about quiver, is it?
Yes.
So yeah, so if you see the scale, if you see the documentation of scale, a documentation of quiver, then the definition of scale is something that is connected to the width of the plot as well. Maybe I can open that for you somewhere. One quiver scale, if you see, it's not the very scale. Where would I get the quiver documentation we want to see? It's not exactly just you multiply. I mean, it's not that the length will be multiplied. It depends on the width of the plot as well. Okay. See, scales the length of the arrow inversely. Okay, so which values did you try out? And one more
20,
thing.
100. Yeah.
Yeah. So when you tried 100, the length reduced, right?
Yeah, and when I gave 1, then it was like infinite.
Yeah. So it scales the length inversely. And next thing is number of data units. Scale is equal to number of data units per arrow length unit. So this is marker size, right? So there is some marker size that we will be providing, right? So in this particular plot, there's a size of each marker that also is used in deciding what should be the arrow size. Maybe you can explore it a little further. Marker size per plot width, right? So there's a particular plot width as well. It will consider both these values in order to decide what should be the length of the vector. Okay.
Okay. Thank you, ma'am.
All right. Okay. So
Ma'am, last question.
Yeah.
Ma'am, suppose we have many features and you told one method to find the redundant features. So what is the method to find the noisy features?
Okay, so there are several ways. So what you are talking about is actually feature engineering. And there are several techniques that are followed in feature engineering. So see, one way is you check so there is a correlation also that you can check. Let's say there are features F1, F2, and this is the target. You might want to see the correlation of F1 with T, the correlation of F2 with T. Okay, that's one way to look at it. Let's say there are several features. Those features which have very low correlation with target, you might want to get rid of them. Okay. Another way is you see this correlation matrix that you can look at, which gives you the correlation amongst each feature. Let's say F1, F2, F3 are there. You might want to see the correlation between F1 and F2, F1 and F3, F2 and F3, and so on.
But ma'am,
If there
in
is
correlation matrix, only the numerical data will be.
Yeah. So there are different other. So what you're talking about is Pearson correlation. There are other correlation metric, methods as well, like rank correlation there is, and chi-square correlation is also there. So Pearson is used for all numerical data, right? This should be numerical, this should be numerical.
Yeah,
If this is numerical, this is categorical, there is some other correlation measure that you'll use. If both are categorical, some other correlation measure that you can look at. So all this is a part of feature engineering, which probably you might have taken a look, or you would take a look in MLP.
Okay.
All right.
Excuse me, ma'am.
Yeah, go on.
Ma'am, I wanted to ask, is attendance the eligibility for the OPP or the certification? I actually missed one session that was on Friday.
Attendance is eligibility for OPP.
Okay.
And OPP is the eligibility for certificate, as you know.
I have roughly 80% attendance, I guess, and it was 90% that was required. Is there any chance that this could be maybe adjusted?
You missed one, is it?
Yes, actually. It was a medical emergency, or else I would have attended.
Okay, there are 5 sessions, right? You
Yeah.
missed one. Okay, I think
Yes.
we should look into it. 4 out of 5 should be
Yes,
sufficient.
ma'am, because
We'll look
I
into
do
it.
also
Yeah.
have an
Yeah, we'll look into it.
Viva for the medium
Okay.
course.
Sure. Yeah, I understand. Oh, you have had a Viva, then that's a very valid reason. You can actually drop an email, and you should not
I
be
had
not
dropped
eligible.
an email actually, but they said it will not be considered for the
Okay.
attendance.
But this 4 out of 5 something, see, 90% is a little, okay, 50% is too less, Deepthi. 90%, I don't know. So if there are 5 sessions and 4 should be a criteria. Let's look into it. We'll check this out. 4 out of 5, yes. Okay.
Thank you, ma'am.
Yeah.
Thank you very much.
Yeah, ma'am,
All right.
if it is possible,
Yeah.
please do.
Excuse me, ma'am.
Yeah, go on.
Yeah, how do we decide if we need to have a dummy feature for the feature set?
Okay, you might want to go with both, one without using dummy feature, another with using dummy feature. Okay. And if you are getting a lesser loss, I mean, you can see whichever way is giving you lesser loss, you can proceed with that. So if you are talking about the application side of it, in sklearn there is a, in several algorithms there is this parameter value which you can set true or false. Okay.
Okay.
Yeah, and you can experiment whichever gives you the least loss. You can proceed with that because it depends on the data set, right?
Okay.
Yeah.
Thank you so much, ma'am.
Okay. All right. I hope we are done. Okay. Yes. All the sessions happened yesterday also. Okay. Thanks everyone for joining. It was a nice interaction. Please keep practicing whatever you are learning here. And there's another session at 3 which you may want to attend. Take care, everyone. Bye.
Hello?
अरे मेरा बेटा बिना बेटा के चल जाएगा स्पीड में नहीं। और उसी में देखो कैसे है उसमें तो वो तू उसकी क्या बोला एसी का उपयोग करें इसलिए पहले ये करना चाहिए ये बात कौन पाया था एसी का बात नहीं एसी में तो अच्छा है एसी को बहुत अच्छा भी तो है लेकिन अभी तक नाम नहीं करना अच्छा लगा दिल्ली को बहुत ज्यादा अंतर नहीं पड़ेगा बोलिए भगत में ये कम साबुन दुकान पे आया था अभी हमको ये एनर्जी का कुछ था लेकिन फिर ये सामने पैटर्न नहीं था अगर मैं काम किया जाता है total correspond given current. Things on the is right. I know when you put someone on chat from there. Here is it's separate. I started putting that from there. So quite funny, but I asked people to learn that. complex value love bestia क्या हाथी में है वो बहन सबसे ज्यादा इसको
पानी के सब उठा के इसमें डाल लो उसको कपड़ा से ठीक है जब डाल के रख दियो ना मिलाते हैं उठा लो हाथ से उठाए दिक्कत ना उधर का बाल हो जाएगा तो उधर पूछते भी ना पाइप नहीं छोड़ा
तकिया रे यहाँ से तो सियाल सियाल
आपके पास ए, टीचर को कपड़ा पहनने पसारी बोले तो हाँ हाँ जैसे पसारो ना साफी कपड़ा का भीगा हुआ है तो वहां पे अच्छा लगेगा चट चट तुरंत सूख जाएगा पोछने के लिए तेज धूप है जाओ पसारो दोनों पसारो हाथ होने तक तो सूख जाएगा भीगा हुआ छोटा छोटा बता अट्टा फटा वहां से किनारे रखो चला था ना पानी चला दीजिए अकबर गिर रहा मुझे तो कहीं सब कुछ